So in this tutorial we're going to look at the combinations approach to solving probability problems. Let's start with this example of a spinner. So we have a spinner that we're going to spin 3 times. So 3 spins then of the spinner. And let's give it a go. Now what we're going to ask ourselves is what's the chance of it landing on, well, okay, in this case amber, let's say exactly once in those 3 spins. What would that look like on a probability tree diagram? So if I drew out my branches, that would be the first spin, second spin, and then the third spin. So 3 events represented on a tree diagram like that. So amber or not amber. If we fill in the outcomes all the way through the diagram, now the probability is very easy to work out. Obviously landing on amber will be a probability of 1/4, but the probability of only once landing on amber, so amber once, is going to be depending on different combinations of going through this tree diagram. So landing on amber 1 in the first spin would be going down this route here and then down the 2 not amber route branches. So we would have 3/4 times 3/4. Now the other possibilities are that it would have not amber in the first spin, and then we would have amber here. In fact, let's circle when it comes up 1/4. So here would be 3/4. And then it would have to be, if it's only once, it would have to be going down this route here, so it's 3/4 again. So every time it goes through this probability tree diagram, we multiply the same 3 fractions together. It's just that they're in a different order. So if we look at our third possibility, if we get it landing on amber in the third spin, it would be here. But again, these first 2 spins would have to give us a probability of 3/4. And every time we're multiplying this together to get the same outcome. So we get 1/4 times 3/4 times 3/4. In other words, what we've got is 3 combinations. So let's just write down 3, multiplying together the same fraction. 1 times 3 times 3 is 9 out of 64, because 4 times 4 times 4 in the denominator. So 3 times 9 64. So the fraction itself, the probability fraction, isn't the difficulty here. It's working out how many combinations there are, which is fairly easy here. We've got just 3 kind of slots, if you like, 3 ways of getting this 1/4, and it's just one thing that we're trying to get. And we'd write this in a combinations format like this. We'd say there are 3 openings, if you like, 3 openings, out of which we're just choosing 1/4. So we call it 3 choose 1. In fact, this is commonly called the choose function. So how many ways of the choosing one thing out of 3? It would be the same as in, say, a small team. If you were electing a goalkeeper, let's say, there were 3 people. How many ways are there of choosing those 3 people? Well, obviously 3 ways. But as the numbers get more complicated, then it's not so clear how many ways there are, and we use this formula. And the calculation we make is the 3 is 3 what we call factorial. Now 3 factorial, if you haven't come across this before, is simply the consecutive numbers 1, 2 and 3 multiplied together. So 3 factorial is 1 times 2 times 3. And the 1 here goes in the denominator like this. And again, 1 factorial, well that will be just 1. So 1 multiplied by the complement. So if it's 3 and 1, then 3 take away 1 is 2. So you get 2 factorial. And that completes the formula for the choose function. So we then have 1 times 2, because 2 factorial is 1 times 2. So the result of this is the number of combinations, which equals 1 times 2 times 3 is 6, and 1 times 2 is 2. 6 divided by 2 is 3, which is the number of combinations that we have of choosing, getting a quarter, if you like, out of these 3 events. So 3 choose 1 will give us 3, and you might in fact be lucky enough to have a choose function on your calculator, which will work in this way. It will be working with it will work out the factorials, and it will give you the number of ways of choosing one thing out of 3. So this is very useful in probability questions, and it's worth us just thinking about, well, what if we said, well, how many combinations are there of choosing 3/4 twice? Because that would be the same thing, so that 1/4 is forced to be there, if you like, and 3/4 twice here, so that 1/4 is there and 3/4 here. Is that the same? Well, 3 choose 2 ought to also be 3. How can that be the case? That looks like this is going to give us a different result. But it should be the case, because if we think of this, this would be, again, 1/4 going up here, and this would be 3/4. So there's only, so this would be 1/4. So there's no possibilities in these branches here of getting 2 3/4. The only way is by going down that branch there. So we've got 3/4 and 3/4 down there. There's a 3/4, 3/4 down here. But if we went down this branch, that would be 3 3/4. So if we're just choosing 2 3/4, there are indeed only these 3 pathways, because that would be 1/4 there. There are only 3 pathways, just as there was for just choosing the quarter. So will that give us a different result? Well, no, it should also give us 3. And let's see how that works. 3 choose 2 gives us 3 factorial here. Underneath, we now write 2 factorial. But remember, in this formula, the complement, which is 1 in this case, 3 take away 2 is 1, goes there. And you can see now this is going to produce the same result, because 1 factorial times 2 factorial is the same as 2 factorial times 1 factorial. So again, we get the 1 times 2 times 3 over 1 times 2, or in this case, 1 times 2 times 1, same thing, but that will also give us 6 divided by 2, giving us 3 combinations. So 3 choose 2 is the same as 3 choose 1. Now finally, I want to think about, what if I went down this route here? So we got 3/4 times 3/4 times 3/4, which we could say is 3 choose 3. 3 choose 3. Okay, well again, we would have 3 factorial in the numerator. In the denominator, we would have 3 factorial, but then we would have 0 factorial. Okay, because the complement of 3 take away 3 is 0. Now 0 factorial is 1. Now, that's a bit of an odd thing, and you might want to look up on the internet why 0 factorial is treated as 1, or just check on your calculator and you'll find that 0, and if you press the factorial key if you have one, will give you 1. But anyway, what would the result be here? Now we should have only one combination So only one branch will give us 3/4, 3/4, 3/4. Let's see if this gives us 1. Well, 3 factorial is 1 times 2 times 3. 3 factorial is 1 times 2 times 3 times 1. So it's 1 times 2 times 3 divided by 1 times 2 times 3. So in other words, it's 6 divided by 6 does indeed give us 1. You also might want to think about 3 choose none. So you could say that going down this branch means we don't get any quarters, for example. But then again, you'll get 3 factorial over 0 factorial. Complement is 3 factorial. So we get the same thing. We get 6 divided by 6. There's only 1. So 3 things chosen from 3 things is the same as no things chosen from 3 things, or 2 things chosen from 3 things is the same as 1 thing chosen from 3 things. So the choose function that we're using here to get these combinations is a very interesting function, and you might want to experiment with all sorts of different numbers. It has a kind of symmetry which is fascinating. Anyhow, it's also a very useful thing, because if we know the fraction, in this case 9/64ths, and all we're trying to do then is find out how many combinations there are, yes, we can draw a probability tree, but we can also use this choose function to find the combinations. It means we don't have to draw the tree, and we can figure out the answer very easily. Okay, let's choose a second example. So if we say that this was problem A, let's choose problem B. This time, instead of using spins, let's use rolls of the dice. So instead of spins, this time we'll have rolls. And think about a 6-sided dice. Okay, and in fact, let's make our numbers a little bit more complicated. Maybe we should think of 4 rolls of the dice. So let's have 4 rolls of the dice. Now 4 rolls of the dice would give us a very complicated tree indeed, and we're probably going to miss some of the combinations. So this is an example where using the choose function, finding out how many ways there are of going through the probability tree is a very good idea. So let's think about the probability of, let's write it here, probability of, well, let's say 6. Probability of 6 coming up once in 4 rolls. So 6 once in 4 rolls. So first of all, let's work out, let me just write that a bit neater. Let's work out what the probability would be. Now, it's worth pointing out that this will only work with independent probability, where these fractions are always the same in each branch, and that means it doesn't matter which order we have them in. If the fractions were different, then we're going to have all sorts of different combinations, and the combinations approach isn't going to work. But when we've got this sort of situation, where changing the order doesn't affect the product of those fractions, then all we need is the fraction, the complete product as we go through those 4 rolls, and then find out how many combinations there are. So 6 comes up only once. So let's just think of an example. So just as we have with our probability tree, let's think of an example as we're going through just one branch. So it would be, well, let's have the 1/6 coming up first of all. Then we would have to have 5/6 and 5/6 and 5/6. So every time that, no matter where that 1/6 comes, we're going to get the same product. So 1 times 5 times 5, that's 125. Now, 6 to the power 4 isn't something I know off the top of my head, so let's just have a look in the calculator. That gives us 6 times 6 times 6 times 6 gives us 1296. So there's the fraction that is always going to come up, but there are going to be, well, 4 different combinations. Let's have a look at those combinations in terms of our choose function. So we've now got 4, choose just 1. We should get the answer of 4. Let's see if we do. So 4 factorial divided by, well, we've got 1 factorial, and then the 3, which is the complement. And 4 factorial is 1 times 2 times 3 times 4, which is 24. And 1 factorial is just 1, just like 0 is just 1, so 1. And 3 factorial is 1 times 2 times 3, which is 6. 24 divided by 6 gives us the 4 that we were expecting. So that just confirms the result that if we're looking for 1/6 coming up, we're choosing 1 from 4, so it's 4 choose 1. That gives us 4 combinations, 4 ways of working through the probability tree diagram. So the answer would be 4 times 125 divided by 1296. So 4 times 125 divided by 1296. So we're going to have 4 times 125 is going to be 500 divided by 1296. And if I divide 1296 by 4, I get 324. And if I divide 500 by 4, I get the 125 back. And that's the highest common factor, so that's as simplified as it gets. I think what would be nice, and in fact might be asked for, is to give the percentage, because that gives us a better sense of what that comes to. So that's the exact form, but the percentage would be 38.6%, let's say, to 1 decimal place. So 38.6%, so fairly likely, just a bit more than a third of a chance that we will get 1/6 if we roll the dice 4 times. And that's a useful result. Very often in a game, you want to know, exactly how likely it is to do something like that. How likely is it that I'm going to roll a 6 if I'm allowed 4 rolls? Okay, let's finish with, if we call this problem A, ignore the spinner and just call that problem A, call this problem B. It's fairly easy to work that out without the combinations function, or the choose function. What would be less clear if we said, let's say 2 6s. So let's roll the dice again, if you like, 4 times. This time, let's say, what are the combinations of 2 sixths coming up? So either we would have a 1/6 times 1/6 times 5/6 times 5/6, or we would have 1/6 and then 5/6, 1/6, and so on. So you can, again, it's fairly simple in this example, but as things get more complicated, it isn't. You should be able to work this out, but let's use the choose function to work it out for us. Okay, so we're asking what is the probability of 6 this time twice, and let's just fit that in here. 6 coming up twice. Okay, so the probability of 6 coming up twice is going to be, for the number of combinations anyway of this, are going to be 4 factorial over 2 factorial, and the complement of 4 and 2 is again 2 factorial. So 4 factorial we've already worked out, that's 24. 2 factorial is 2, so 1 times 2, and 2 times 2 is going to be 4. So the number of combinations of 4 choose 2 is 6. Okay, Now, back to our 1/6 times 1/6 here gives us 1/36, or let's just multiply right across. So 1 times 1 times 5 times 5 is 25. Okay, and again, it's out of 1296. So we've got our fraction. All we need to do is multiply the 6 combinations by the 25 divided by the 1296. So this time we get 6 times 25, which is 150, divided by 1296. And I'm going to use my calculator to simplify this one, so I don't have to do the highest common factor and so on. So 150 divided by 1296 is going to give me 25. There we go, 25 out of 216. And again, to give a sense of that, if I press my SD button and work out the percentage, I've got 11.6%. So far less likely that I'm going to get 2 6s than it is that I'm going to get 1. And that intuitively makes sense. Okay, so it's very important that we understand how this choose function actually works. Now, in the example of the dice, where we had 4 events, so 4 rolls of the dice, but we only wanted to find the combination of exactly 2 6s, so 2 6s. We could draw out a tree diagram, and I've actually drawn it out here, but it's quite a laborious thing to do. And as the events get larger, the tree diagram gets more complicated. It's not going to be viable always to do it in this way. Nevertheless, I've done it for this one, so we can see that there are, well, there's 6 6 and then no 6s here. That gives us exactly 2 6s. This pathway here gives us exactly 2 6s, and so on down here, and I've ticked now 6 branches, so it looks as though there are exactly 6 combinations of 2 6s in 4 rolls. But the combinations formula that we've just been using gives us a more exact definition, and it makes us confident that we are actually getting the right number of combinations. Okay, but how does it work? Can we rely upon it every time? And where does it come from exactly? Well, what I'm going to do is use this as a case study. So let's think about the 4 rolls of the dice as 4 cups. Okay, so we've got 4 cups representing 4 rolls. And what we've got to get in those 4 rolls is 2 6s, exactly 2 6s in those 4 rolls. Now, to think about how we get the formula for combinations, we have to start with the formula for permutations. And that's why I've coloured this dice red and this dice white. So the formula for permutations in fact looks like this. It's n factorial, so in this case 4 factorial, divided by n minus r factorial. In other words, 4 minus 2 factorial. So let's understand how that works, and then we'll move to the combinations formula. Okay, so let's draw out our cups here so that we can see very clearly how we can fit the 2 6s into the 4 rolls. First of all, let's just start with our red dice then, because we're working with permutations here, so it's important what order we roll these dice in. So first of all, we can see very clearly that if we try and position the red dice into these cups, there are 4 positions that it can be that it can come up in. So if I look at the 3rd row here, I've got the 3rd position, and I've got another possibility where it could come up in the 4th position. So there we go, 4 positions then for the red dice. If I think about the white dice now, there are only 3 positions left in this scenario. So if the red dice is in the 1st position, the white dice can only occupy the second, third and fourth position. So it could go here, it could go here, or it could go here. And that's going to be the case for all of these rows. And that gives us our first answer for how many permutations there are. If I have 4 rolls of the dice and I'm looking for 2 6s, exactly 2 6s, then I can see from drawing it out that it must be 4, as in the 4 rows here, times the 3 for the white dice. So 4 times 3, in other words 12. Now let's have a look at the formula and see if that gives us 4 times 3 equals 12. Well, the formula has in the numerator n factorial. And n factorial is just, factorial means 1 times 2 times 3 times 4, or 4 times 3 times 2 times 1. So it doesn't give us the 12 that we want, but it does give us 4 times 3. So the denominator must be removing the 2 times 1, and indeed that's what it does. So we've got n minus r, so it's 4 minus 2, we've got 2 factorial in the denominator. So if I draw this out now, according to the formula, we should get back to the 4 times 3. So the formula says n factorial, so 4 factorial, which we're writing as 4 times 3 times 2 times 1. And we divide by n minus r factorial, which is 1 times 2, or 2 times 1. So you can see that this cancels to leave us with exactly what we wanted, 4 times 3, in other words 12 permutations. Well, that's great for permutations, but in fact when we're thinking about how many combinations, in this particular problem we don't want permutations, we only want combinations. If you think of the example of drawing cards from a deck, that would be the same sort of thing. When we're looking at our cards, we're not interested in what order they came in. And in this example, when we're looking at our dice, we just want 2 6s. We don't care if the red dice came before the white dice or the white dice came before the red. They're exactly the same. So there must be a lot less combinations than there are permutations. The question is, how much less? Well, let's have a look at the repeats in our diagram that we've drawn out here. If we think about, first of all, this position here, then that's going to be repeating when the white dice fell in this position here. So in other words, this row is no different now to this row here. So we need to eliminate this permutation. Again, if we think of putting the white dice here, then it's going to repeat this position here. And same here, that repeats this one, here, here, and finally here. So how many is that? Well, it turns out that for every combination, there are r factorial permutations. For every combination, there are r factorial permutations. So to eliminate the repeats here, what we need to do is divide by r factorial. So the combinations formula, NCR, is n factorial over n minus r factorial, but with another factor in the denominator, in other words, r factorial. So when we divide through by r factorial, we get the number of combinations. Okay, let's see how that works then. So we've now got 4, choose 2, giving us, again, 4 factorial, according to our formula. So times 3 times 2 times 1, divided by the n minus 1, so that's 2 minus 1, 2 times 1, sorry, 2 times 1, which gives us then our number of permutations, in other words 12, but we're multiplying now by r factorial, so that's 2 times 1 again, so 2 times 1 times 2 times 1. And we can cancel here and here, giving us the permutations part of the formula. And here we can cancel the 4 and the 2, so divide by 2, giving us 2 here, 1 here. Now we've got 2 times 3, 6 divided by 1, so the number of combinations equals 6. And we know that's correct because we've checked with our tree diagram. So when you want to work out the number of combinations in a probability problem, the choose function works every time, and this formula here turns out to be one of the most useful formulae that you need when you're tackling probability questions.